In the previous video, we had discussed about the characteristics of the VCO, and we also have seen the PLL in a log condition. How does it looks like? Okay, and also we have seen the example of a VCO in LTspice. So today we will discuss about the type 1 PLL and also its loop dynamics, and also we'll see its simulation in LTspice. Okay, so as we have seen previously, the phase detector can be implemented by a simple JOR, and of course it has to be followed by the low pass filter for averaging. Okay, so finally we want to average it and get a average output. So for low pass filter we will be using a simple RC circuit. So we know that a simple RC filter is a low pass filter. Of course we can go for more sophisticated low pass filter, but in this example we want to just use a simple R and C, and the average value of this PD will be fed to the VCO. Okay, and of course this is my input V in, and this will be the output of the VCO. So we can connect with a divider and get the multiplied output, but in this example we just want to go without a divider. That I just want to, or they have the same the phase difference between them is constant, or the frequency is the same. Okay, so and this is what we want to see. In the LTspice we have seen how to simulate a VCO, how to simulate a JOR. Okay, and of course we can just add this RNC and we can do the simulation of this PLL in LTspice. So let's go to the LTspice and see how does it looks like. So this is my simulation test bench for a type 1 PLL. So it is called a type 1 PLL because of one reason that we will see eventually when we'll discuss the loop dynamics. So I have a JOR here which we had seen last time, and of course I have used an RC filter of 200 ohms and 50 nanofarad capacitance, and of course this is the VCO that we have seen in the last lecture. Okay, and I want to run a transient simulation, so I have given the SPICE directive of 250 microseconds. Okay, so this SPICE file will be available in the website, so you can download and do the simulation yourself and vary different parameters and try out yourself. Okay, so let me do the simulation and try to see how does it looks like. So it's simulated, and let's see what happens to this control voltage. Okay, so this control voltage is a very good parameter to to identify whether the PLL is working or not. So if you see here, the I'm using a sine wave generator here. If I see the property, so it is generating a 1 megahertz. Okay, 1 megahertz, and these are the parameters. Okay, and if you see here, the VCO characteristics, it is same as the one that we had discussed last time. Okay, so at 0 volt it is generating a frequency of 0.5 megahertz, and at 1 volt 1.5 megahertz. So as we have seen in the last class, that to generate a 1 megahertz frequency, the control voltage should be 0.5. So this is what PLL should produce, right? The control voltage V1 should be 0.5, so that the output frequency also becomes 1 megahertz. So this is the waveform. Okay, so we can see here that initially it was at the V1 voltage. Initially it was at 200 millivolt, because the initial condition of V1 IC is the initial condition dot IC, and VV1 voltage V1 should be 0.2 volt. So that is the initial condition, and it initially started like this, and we can see how the control voltage is varying, and eventually it is going to this value, right? So after a good amount of cycles, so we can see that the this is going to this value, and of course we can find out the average value of this waveform. So you can, if you see here, if I move around the cursor, it is coming around 500. So you can see here this number y, that is 500, and of course I can zoom it, and if I just do the control, press and hold the control button key, and just if I click the waveform, if I click here, that from 60 microseconds to this 250 microseconds, it is giving an average, and the average value is almost 500 millivolt. Okay, so basically it is producing, it is producing after some time, it's getting settled, and it is producing the same frequency as the input. So input is 1 megahertz and the output is also 1 megahertz. If you want, we can plot these two waveforms and see. Okay, so these two waveforms are plotted. Let me delete the V1 now, or maybe I'll just add another plot plan and then plot the V1 here. Yeah, V1 I'm plotting here. I will delete the V1 from, so I'm deleting from here and here. Okay, so yeah, so you can see here initially when the control voltage V1 was not settled, we can see that there is a lot of difference between the V in and V out. So if I zoom in here in this waveform, so it was not settled at this time. So we can see that there is, the phase is not constant, right? Sometimes it is less, sometimes it is more. It's trying to settle, okay? And eventually, as we go to the this point, this time, so we can see here that the it is almost constant. The phase difference between these two waveforms, the blue is the input and red is the output. So you can see that it is almost the phase difference is constant, and these two have the same frequency. Okay, of course we can do the FFT of the from here. If we want, we can do the FFT of the V out. Okay, and also we can see that, so to do the FFT view, FFT, okay, FFT of I want to see that for the V out signal. So FFT is a better way to see the frequency. So you can see here that this is oscillating at a frequency of almost, I should say that 1 megahertz. So this FFT point, so it's operating at 1 megahertz. So this is the output V out. Okay, yeah. So we can say that the PLL is locked, and the output frequency is now same as the input frequency. Okay, but if you see here, if you see the loop dynamics, the V1 or the control voltage of the VCO, it has this ringing pattern, right? It is getting settled, or this V in equal to V out only after a time period of around 60 microseconds. Okay, so it is taking a time of 60 microseconds for settling. So this is called the settling time period, and we'll also see why this loop behavior. Okay, how can we understand this one? Like, why is this ringing? Can it be faster or can it be smaller? And also we can see that there are small ripples here. Still there are ripples, right? And is there any way that I can reduce this ripple? So of course we can increase this one and reduce the ripple. Okay, so if I increase this one to be, maybe make it double. Okay, and just run it. Yes, so it's becoming more smooth. We can see that it's becoming more smooth. But now if you see the settling time has increased, right? It has increased from 60, previously it was 60, but the PLL is taking time for locking, and it is going more than, so here the time is around 100 microseconds. So it has increased to 100 microseconds, and we can see that it is more smooth. Whereas if I make it very less, maybe just 20 nanofarad, okay, so we can see that yes, the settling time is very small, it's just 24 microseconds, but we can see that there's a lot of noise, that the control voltage is still jumping. The average value is not very clean. So these are the consequences of increasing or decreasing the capacitor. Okay, so to understand this loop dynamics, that why by increasing this capacitor it is taking a longer period of time to settle, that we will try to see by understanding its loop dynamics. And also we'll see that if there is change maybe in the frequency, if there's a step in the frequency, how much time it is taking to settle it back. Okay, so those things we'll try to see. Okay, so initially also we can see that there's a difference in the when we started with 0.2, there's a difference between the the two frequencies, and it took some time to settle. Okay, so these are the things. To understand these things, we need to model the behavior of this PLL in a we need to understand it in a from the control system perspective. Okay, so we need to model and get the S-domain model of this PLL and see how what happens when there is an abrupt change in the either in the input frequency, how the output is tracking, and why the PLL is taking longer time to settle when I increase the capacitor. So to model this whole thing in the S domain, of course, we know already the S domain transfer function of a simple RC low pass filter. So first of all, we should try to model the VCO in the S domain. So let's try to understand the model of the VCO in S domain first. Okay, so basically what we are trying to do now is, so we have this VCO characteristics. So we have the control voltage V cont, and we have the omega out. This is what we had seen in the previous lecture. And we have this omega naught, and we have the slope, which is the KVCO. Okay, the slope delta omega out by delta V cont is the KVCO. So basically here what we are trying to do now is, suppose my VCO is settled and my voltage, V control voltage, has reached this V1. Okay, has reached V1, and and of course it is oscillating at a frequency of omega 1. So in this case the V1 is equal to we have seen it is 0.5 volt, and this omega 1 is 1 megahertz in the example of the LTspice that I have shown. Okay, so now what I want to see is loop dynamics means the small signal analysis. Okay, just like we do a small signal analysis for a circuit, we want to know the behavior, that if this is this is like a DC value, and if there is a change, right, if there's a small change additional on top of that, let's call it a small V1, then how much my omega is changing. Okay, so for a small V1, like if the control voltage is oscillating by small V1, basically that there's an error, then how much my how much my omega is changing. So this is the loop dynamics that we want to see. And of course, if there is a change in the control voltage, there will be a change in the omega, and there will be a change in the phase, output phase of the VCO. So the instantaneous omega that we see is basically omega is equal to d phi by dt. So because of the change in the control voltage, omega is changing, and to find out the change in the omega, we can just if we know the phase, we can just differentiate it. Okay, or I can write it as implies my phi t, if I just rewrite, is basically integration of omega t dt. I'm just showing the t variable here. We can show here as well that the instantaneous, because it is now dependent on the time, it is changing with time. Okay, so now of course, therefore I can write my omega or the phi out because of the change in the omega can be written as, you know, uh, omega t dt, omega out. Okay, this omega out by dt. Okay, and since we know that omega out is omega out t is equal to omega naught plus k VCO by V cont, and this is also changing with t. Okay, so this is changing with t with time, so I can write this as implies this is omega naught plus k VCO V cont t dt, the whole integration. Okay, and since omega naught here is a constant, it's basically the y-intercept, so definitely I can take this term outside, omega naught t out of the integration. If I integrate just the delta t, it is t, and here I have, of course, the KVCO is also constant, it's a slope, so it also comes out KVCO, and what I have here is V cont t dt. Okay, so now if you see the V cont here, V cont is V cont t is V cont t in this case is V1, which is also again a constant DC. This is the DC biasing condition. Okay, plus we have only the small vt which is changing with time, the small signal basically. Okay, so this I can write again, I can write, if I substitute this V cont with v1t and vt, it is something like, you know, omega naught t plus k VCO. Again the constant, this v1 comes outside, and this is integration of dt plus again k VCO integration of v1t dt. Okay, or you know, what I can write is as omega naught is equal to, again the integration of t stays, and then I can just sum it dt. Okay, so now of course this is my this is the, you know, this is the, you know, when there is no change, so of course this is the operating frequency omega naught by kVCO into v1, but if there is a small change, then this will be shown something like this, or my v out which is coming out of the PLL is, I can write it as some sine, it's a sine wave, right? So phi out t, okay, right, or v out is, I can write it as vm sine omega naught plus kVCO v1 into t plus kVCO small v1 t dt. Okay, so this is how actually the output of the, you know, the PLL or output of the, you know, this is my v out, this is the exact expression of the v out with time. Okay, so now if you observe here, okay, this is basically, we will say that this is an excess phase. Okay, so this term is the excess phase because of the, you know, excess phase because of the additional small signal v1t. Okay, so the excess phase, or we can see that this is the excess phase that it is generating, right? This is my phase in this steady state condition, but if there is some change in the transient behavior, so this is the excess phase. So what I can write is as I can define that the excess phase The additional phase EX is basically this one, KVCO integration of V1T dt. So because of the small change in the control voltage, I have an additional excess phase. So what I can write is, now if I try to convert it in the S domain, implies, right, this is of course T, excess phase is also changing with the time. So if I try to convert in the S domain, then what I have as, and of course this KVCO is a constant, KVCO, and the integration become 1 by S. Okay, so therefore the excess phase that the VCO is generating because of the change in the control voltage of the VCO is given by KVCO by S. So this is a very important expression. Yeah, so many of the confusion arises because of this one, that the output of the VCO is an integration of the control voltage. No, this is not true. This is only the excess phase. The excess phase that the the VCO is generating is the integration of the change in the control voltage. So that is what we have to remember. Okay. Yeah, so this is the model of the VCO. So this is the model of the, I should say, the small signal model of the VCO. The small signal model of the VCO for a small change can be expressed by something like this. So if I try to draw the whole thing, like, because of there may be a there may be a constant phase difference between these two, and if there is a small change, small error in the phase difference, right? So then that will lead to a small change in the, I should say that the control voltage, as well as in the output phase. So the complete model of the PLL is something like this. Okay, so I do have the low pass filter. Okay, so RC, and we know that for an RC, this is a simple, the S domain is 1 plus S by omega LPF. So where omega LPF, we know that it is 1 by 2 by RC. Okay, and after this I have my VCO. So which is, as we have seen, it is KVCO by S. Okay, and of course this is my output, the output phase out, and of course this is again, this is just I'm showing as E because this is an error. Okay, this is not the exact phase. Okay, and similarly in the input side also. Okay, and here also the input will be like, if there's a change in the input phase. Okay, so this we are representing by a phi and E. Okay, and of course there is a of course there is a feedback part. So this okay, so let's try to understand this transfer function. Okay, so the open loop transfer function is something like this. If there is no feedback, it is open. Is, if there is no feedback, it's very simple. So of course here I have one more block. Sorry, I have forgotten it. So it is the I have the phase detector as well. So and the phase detector will have a gain. Okay, so that is represented by we have the PD, right? So the before the low pass filtering, we have the KPD. So which converts the phase difference information into the voltage. So this is the KPD. Okay, So if I try to see the open loop transfer function, it is kpd into this transfer function, which is 1 by 1 plus s by omega lpf, plus we have the, not sorry, plus, it's a product of the kvco by s. Okay, so now, yeah, so if you see here, this transfer function has one pole at the origin and one pole at omega lpf. Okay, so because it has a one pole at the origin, that's why this kind of PLL is called the type 1 PLL. So we'll see the type 2 PLL also, where the open loop transfer function has two poles at the origin. Okay, this is called type, so it is called type 1 PLL because it has one pole in the origin. That's why it is called the type 1 PLL. Okay, so now we have done the open loop transfer function, and we can get the closed loop transfer function as well. So which we know that it is just because the division factor is just 1, so it is just 1 HS open by 1 plus HS open. So if I try to write it down, it looks like something like this. You can try out yourself. So if I do this and do a simple, VCO, okay, so the S will get multiplied everywhere. Okay, so it will be S square omega LPF plus this multiplied S, plus we have the 1 plus, right? So it becomes KPD KVCO. Okay, so this is my closed loop transfer function. So which is basically my phi out error and by phi out phi in. Okay, and since the phi and the phase and the omega are linearly related, right? So it's just the the omega is basically I should say that the differentiation of the phase. So what we can say is that the omega out, again the error, and omega in error, or I should say that instead of error I can say better way to call it is the change, right? The delta omega out by delta omega in. So yeah, the change in omega out by change in omega in, so it can be written as we can write the same thing here, KPD by KVCO, and we have the the S square omega L PF plus S plus KBCO KPD. Okay, yeah, so of course yeah, so what we can say is that whether it may be the change in the phase out by change in the phase in, or change in the omega out by change in the omega in, because they are linearly related, so the transfer functions remains the same. Okay, so let's from now onwards, let's just call this whatever as HS. Okay, HS, and this I can maybe a little bit rewrite this whole transfer function as omega n square S square plus twice eta omega n s plus omega n square. Okay, so this we are trying to express as a second order system. Okay, second order system where we know that where omega n is equal to omega LPF, KPD, KVCO, okay, and eta is equal to half omega LPF by KPD by KVCO. Okay, so all the whatever this is a standard equation that we use in the control system to define a second order system, and so all the formulation for the second order system is applicable here, and as we know that for eta greater than 1, the system is overdamped, and for eta lesser than 1, system is underdamped. Okay, so by this we can analyze the system, the PLL, and we can design like whether we want to make it overdamped or underdamped. Okay, so all these things we can find it out. Okay, and whatever the techniques that we use to analyze at the second order system is all applicable here. But now how do we visualize it? Like we have seen when we are doing the simulation, we are seeing the control voltage, right? So we want to see or we want to understand the behavior of the PLL by seeing a control voltage, and which is also is a valid. Okay, why? Because we know that from a VCO we know that omega out is equal to omega naught plus KVCO by P cont. Okay, or we can say that therefore if I do the differentiation, d omega out by maybe dt is equal to this becomes 0 plus KVCO dV cont by dt. Okay, so I can of course cancel the dt as well. So what I can say is that therefore, and if I just instead of d, if I write delta omega out is equal to KVCO by delta V con, change in the V con, or we know that this is nothing but KVCO into the small v1, which is changing with time. Okay, delta V con. Okay, so now what we can write it, right? If I substitute this omega out in the equation here, okay, so we know that this whole equation is HS. Okay, so we know that delta omega out by delta omega in is equal to HS. Okay, and that means I can substitute this one with this one. Okay, so that means my KVCO into V1 by delta omega in equal to HS. Okay, or implies my change in the control voltage because of the change in the omega in, we can analyze it just by this happens to be the KVCO dot HS. So by seeing the behavior of the HS, right, seeing the behavior of the HS, we can see how much my V1 is changing. Or what I can say is that by seeing the V1 also, we know that how the omega out is changing, because they are, we can say the change in the omega out is directly proportional to the change in the V1. Okay, so just by seeing the change in the control voltage, we can say how the frequency is changing. Okay, so that's why when we are this is the reason when we are analyzing the PLL, we just see the change in the control voltage. Okay, by seeing the change in the control voltage, whether it is settling or not, or what kind of ringing it is having, right? We can know the behavior, that this is same as the behavior of the HS. Okay, for a change in the omega in. Okay, for example, like if there is some step change in the omega, okay, omega in. So this is my omega in, and this is my delta omega in. There's a change in the okay, there's a change, right? And then from here we can easily find out, like, how my V1 is changing, right? So if I find out how my V1 is changing, so that behavior will also, like, mostly what we try to see is the settling time, right? How much fast the V1 is settling, okay, and to a constant value, right? And of course, I'm not going to the mathematics of that, but according to the mathematics, we can know that the decay behavior is very much is follows this expression, e power eta into omega n t. Okay, so the exponential decay, again, this is from the standard control system theory, that the exponential, it is there is an exponential cell decay in this ringing, especially for the underdamped response, and the decay is governed by e power minus eta omega n t. So that means if I try to make this eta omega n very large, that means that the exponential decay is going to become faster. And if we just substitute this, if I substitute and also if I just multiply eta and omega n, I'm going to get a relation something like this, LPF, or I can say it is half into 1 by RC. Okay, so the RC filter. So that means the decay, or how fast my the PLL is settling, is very much dependent on the, I should say that on this. Okay, so eta omega n. That means if I am making this RNC large, okay, that means my eta omega n is going to become small, and that means it is going to take longer time. Okay, so you see, we need to make the C large to make the ripple smaller, but we have seen that if we make the C larger, then what is going to happen is that the settling time is going to become longer. So this is what we have also seen in the simulation that I have shown before. So hence we can say that there is a trade-off. There is a trade-off between the settling time and ripple of the control voltage. Okay, so the if I make the C large, the ripple is going to become small, but from this expression we know that if the capacitance is increased, my eta omega n reduces and it takes a longer time to settle. Okay, so again I'll just like to show back the demonstration. Okay, so this was the 20 nanofarad. Okay, so I have a lot of ripples here, and the settling time in this case is 24 microsecond, and if I increase this C to maybe 100 nano, okay, my ripple voltage is going to reduce, or this V1 ripple voltage is going to reduce, but at the same time we can see that it is taking longer time to settle, almost 140, right, 140 or 130 around, it is taking time to settle. Okay, yeah, so and of course we can see that this is the ringing. Okay, and from omega n we can also find out the oscillation frequency of this ringing. Okay, and we can use this formula to design the PLL provided depending upon what is the specification that we have been given. So what should be the ripple voltage, how much it should be, and what should be my settling time. Okay, so I suggest that you download the LTspice file from the website and do the simulation yourself and see that this the behavior follows this expression. Okay, also you can try to based on the you can give some values of these, and you can try to simulate this behavior in the MATLAB as well and see that the loop response, okay, the response or the behavior of the control voltage is matching with whatever you are getting in the LTspice. So with this we'll end this lecture. Thank you.